Presenting our first paper in the application and ML model design session is Guangyuan of Princeton University, describing smartphone imposter detection with behavioral data privacy and minimalist hardware support. So I'll hand it over to you, Guangyuan.
And I'm a PhD student at Princeton University. Today, I would like to introduce our work of smartphone imposter detection with behavioral data privacy and minimalist hardware support. This work is done together with Professor Ruby Li and Zecheng He. So a smartphone imposter is an attacker who pretends to be the real user of the smartphone and uses the smartphone for malicious purposes. The sensors in the smartphone have been used for imposter detection, especially the motion sensors such as the accelerometer and gyroscope. However, many existing machine learning methods rely on manual feature extraction. Also, in order to achieve real-time imposter detection on smartphone, the detection program needs to contain with other applications for hardware resources such as smartphone CPU or GPU. In this paper, we explore whether deep learning algorithms without handcrafted feature extraction can achieve good accuracy, and how a low-cost hardware module can be designed for imposter detection algorithms. We consider two scenarios for imposter detection. The first case is a cloud-based scenario, which is also called imposter detection as a service. In this scenario, the data from both the real user and other users can be used for training. The algorithms we consider include the state-of-the-art kernel rate regression, which extracts 7 features per sensor from the time and the frequency domains. Another machine learning algorithm we test is the support vector machine. For deep learning algorithms, we use the multi-layer perceptron. We use the working behavior in the HAPT dataset to identify each real user from other users. The result shows that the SVM algorithm performs better than the KR algorithm, and the MLP algorithm can achieve a comparable accuracy of over 97% as SVM. The second and more important scenario is the privacy-preserving scenario of local anomaly detection. In this scenario, no shared sensor data is available from other users, and only the real user's data can be used for training. We test the commonly used machine learning algorithm one-class SVM. We also use the deep learning method of long short-term memory to model the normal behavior. The LSTM-based approach uses the current accelerometer and gyroscope readings to predict the next sensor readings. To decide whether the testing sample is from the real user or not, the most straightforward way is to compare the average prediction error with a threshold. However, we show that using the prediction error distribution, or PAD, is critical to improve the accuracy. Here we show the workflow to use the statistical KS test to compare the PAD for classification. In the training phase, the LSTM cell learns to predict the next sensor reading. In the testing phase, the prediction errors can be observed by comparing the predictions with the real sensor inputs. The first way is to consider the testing sample abnormal if the average prediction error is larger than a threshold. On the other hand, to use PAD, the reference PAD needs to be collected in training. Also, all the prediction errors within the test window are collected as the test pad. This reference pad is compared with the test pad using the KS test to detect anomaly. The detection accuracy in the privacy-preserving scenario is shown in the table. The LSTM threshold models in the table are to compare the average prediction error with a threshold. The PAD LSTM both models collect multiple reference pads in training. The final classification result is computed by doing a major majority vote of the multiple case test results. The numbers next to the LSTM model types are the size of LSTM cells. The result shows that the LSTM threshold do slightly better than the one-class SVM. LSTM pad models perform much better than the previous two models and increase the accuracy from about 70% to more than 87%. The result also shows that a higher accuracy can be achieved if a longer detection time of 4 seconds is allowed. We then explore the minimalist hardware support for imposter detection. We implement the SID module, which stands for Smartphone Imposter Detector. SID is designed with the following motivations. First, and most importantly, we want the self-contained hardware module without pre-processing or post-processing on other hardware units, such as CPU. The benefits include reducing the attack surface, minimizing the impact on normal usage, and reducing the performance overhead. We also aim to make the design as small as possible for the resource-constrained devices, while being flexible to support various machine learning and deep learning algorithms. While being small, SID is designed to be scalable for more performance in the future. Here is a block diagram of the prototype SID module. This module is programmable and can read macro instructions from the instruction run. The data and model parameters are stored in the data run. Each macro instruction will initialize a finite state machine in the decode unit, which controls the automatic looping of vector or matrix operations. The decode unit also generates the control signals for the following pipeline stages. The 3 execution stages are for table lookup, multiplication, and addition respectively, and each stage has 4 parallel data paths. Without adding additional stages to perform the linear interpolation of selected nonlinear functions, we save the design cost by placing the lookup table stage in front and reusing the multiplier and adder stages. The adder stages can also be reused either for parallel addition or as an adder tree for accumulation. We also include a local scratch pad to store intermediate results and reduce the external memory accesses. The SID module is programmed with macro instructions which encode the looping of vector and matrix operations. The mode field encodes the type of the operation that we will explain later. Instead of using fixed size registers, we use the block runs to store the 2 input operands, X and Y, and the result Z of each instruction. The SID module has a finite state machine to control the loop and the vector or matrix. For vector operation, only the length field needs to be used, while the matrix vector multiplication needs to use both fields to specify the size of the matrix. The benefit of SID is that the parallelism of the hardware is transparent from the programmer's view, as hardware manages the execution. This means that the same set of macro instructions can be used in different SID implementations with different numbers of parallel data paths. We implement the operation primitives that are needed by the algorithms which have good accuracy. The algorithms are the MLP and SVM algorithms for the cloud-based scenario, and the LSTM-based algorithms for the local anomaly detection scenario. The basic operations such as matrix vector multiplication, vector addition, vector subtraction, and vector multiplication are needed by most of the algorithms. The nonlinear functions we support are sigmoid, tangent H, and exponential functions. The exponential function is needed by the SVM algorithm to compute Gaussian kernel. the sigmoid and tangent H functions are needed by the MLP algorithm as the activation functions, and also the LSTM algorithms to compute the LSTM gates. We have the squared L2 norm operation to compute the Gaussian kernel for the SVM algorithm and the prediction errors for the LSTM-based algorithms. The vector set greater than is for general comparison, including the comparison with a threshold. Two additional primitives to compare a vector and a scalar and find the maximum absolute value are needed to perform the KS test, which we will explain later. The PAD LSTM method needs a combination of LSTM and KS test operations. We show our implementation to perform KS test in 5 main steps. In the beginning, we have the reference prediction errors from the training process and the test prediction error. The first step compares one scalar, which is the test prediction error, to all entries in the vector of reference prediction errors. In the second step, the contribution by this test error is added to the test histogram, which represents the test pad. And after we repeat this for all errors in the test window, we do a vector subtraction to compare the test histogram and the reference histogram. Then we find the maximum absolute difference in step 4 and give the result in step 5. The step 1 and step 4 are the 2 new primitives we add for KS test. We run the selected algorithms on the SID module and measure the execution time. The bars are the execution times, and the red curve is the accuracy. We notice in the IDAS scenario, the MLP models can achieve a similar accuracy as SVM, but have lower execution time. The PAD comparison adds to the execution time, and the impact grows with the window length we use. However, all the execution time are under 4 milliseconds, which is much less than the 20 milliseconds to collect a new sensor reading, and can hence meet the real-time detection requirement. It should be noted that the time to detect an imposter is the window length plus the execution time. And we show here that the execution time is negligible compared to the sensor collection window. We also measure the memory usage to store the model parameters. In the IDAS scenario, the MLP models uses less memory than the SVM model, and the MLP with 2 hidden layers performs better than a larger MLP with 1 hidden layer. PAD has very small impact in terms of memory usage for both window length. We show the major difference in size between the minimalist state module with the performance-oriented accelerators. As the LSTM is critical to the privacy-preserving scenario, we choose 2 other RNN accelerators that are also implemented in FPGA. The RNN accelerators have higher parallelism and computing power compared to the SID module. But SID can be a better alternative to provide just enough performance with the flexibility to support more algorithms and minimize the hardware cost. We use a conservative 32-bit fixed point number design, but our lookup table, flip-flop, and DSP usage and power consumption are already 1 or 2 magnitudes smaller than the large-scale accelerators. In conclusion, we show that the deep learning algorithms without complicated feature extraction can perform better than the traditional machine learning methods for imposter detection. We show that using and comparing the paths is critical to improve the detection accuracy for LSTM in the privacy-preserving scenario. We also designed the Minimalist SID module to support the whole detection algorithm by providing only the necessary hardware primitives. The SID module is small compared to the dedicated accelerators, but is scalable for more performance. So that's the end of my presentation. Thank you all for being here, and I'm happy to take any questions.
I have a question. I'm wondering, so you built this SID hardware accelerator. Did you try just a pure software implementation of this? I'm wondering, what's the benefit of the hardware accelerator versus just running it on a microcontroller or a core inside the phone?
Yeah, I think that's a very good question. So we have run some experiments, brief experiments on smartphone to run the algorithms and models. But I think the tricky thing is that we need to periodically interrupt the execution of the processor to get the sensor inputs and run the model, which is actually once per 20 milliseconds. So it is actually a very frequent interruption to the normal execution. So I think it can be a good future work to analyze what is the performance overhead or impact to normal application. But we still think it's a good opportunity to have dedicated hardware modules so that the major CPU is not frequently interrupted.
Nice. Yeah, so a related question has come in here on the channel, which says, can you elaborate on the complexity of the instruction processor? And the questioner, notices that it only required a small number of FPGA resources, and as far as they're aware, like an in-order RISC core uses like 10 to 15,000 gates. So I guess the question is around like, what's the complexity of the processor?
So I think in terms of the data paths, the arithmetic units are kind of similar to what we have in a typical simple processor, but the control logic is different. So we could see that it is specifically designed to support the loop of some similar operations on a vector or matrix. So it means the loop is controlled automatically and efficiently. So we do not need to have any control instructions to jump back to the beginning of the loop and restart. So it saves the throughput of the processing unit, and it does not have the complicated hardware structures such as predictors or some other structures for the general purpose processing. So we think it should have lower cost and more higher throughput compared to the general purpose processor of the same size.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse, EMSA, Gray Matter Labs, Green Waves, HiMax, Imagimob, Latent AI, Maxim Integrated, Quixo, Reality AI, SensiML, Silicon Labs, Sentient, Google TensorFlow, XMOS, and lastly, silver sponsors, Edge Cortex, Hotg, and Synsense.